Good afternoon. My name is Michał Bessler. I'm machine vision engineer in Adaptive Vision team. During this presentation, I would like to talk with you about the camera calibration. Why do we need it? When do we need it? How we can perform the calibration. And later, in the second part of my presentation, I would like to show you how the calibration process looks inside Adaptive Vision Studio. Okay, let's get started. So first of all, what is this camera calibration? Generally speaking, we can say that it is creating an image deformation model. But what does it mean exactly? So generally speaking, each lens which came to our factory or which we use in our machine vision systems are not perfect. They are not ideal. And when the lens is a little bit cheaper or when the focal length is rather short, like 6, 4, 4.5, 6, 8, 16, depending on the lens quality, we are experiencing a quite significant deformation on the image. You can see that on the right side of our slide, that the top image and the objects on the top image are not along the straight parallel lines, but rather the objects are at some kind of arcs. That's the very well visible lens distortion. And the calibration is a process of uh, finding that distortion and removing it, so that later we can work on such much better image. Another task related to the calibration is aligning the image coordinate system with world coordinates. We can say that image acquisition is a process of discretization of continuous objects on our scene into the finite number of into the limited number of elements called our pixels. In this situation, we would like to know what's the conversion ratio between the pixels and millimeters. Okay, so when do we have to calibrate camera? First of all, one of the main reason or one of the group of applications where when calibration is crucial is gauging. Every time we would like to express the information in real world units, we have to perform the calibration. Also, when we would like to perform a very precise calibration, if we would like to perform a very precise measurement, we also have to perform a very good quality calibration. Another group of application is related to the robot guidance, robot navigation. In that case, we would like to combine the robot coordinate system with our camera coordinate system so that we can information in pixels transfer to the world object and send meaningful information to about, for example, the picking point to our robot. Okay, that's a fraction of applications where the calibration is necessary. And let's see when we should calibrate the camera. In fact, I I don't recall any application where calibration is harmful for our system. Once it's performed correctly, it will just help us. The only one idea which came to my mind is the execution time uh, influence of our complete inspection routine. However, the final remapping after the calibration is extremely fast, and it should fit to most uh, and even very time limited applications. So I would say that we should calibrate camera whenever it is possible. First of all, because we are able to remove lens distortion, and objects on our image will look less distorted, and it will probably be easier to create the algorithm, inspection algorithm. Another type of application are related to the perspective distortion. Let's imagine the situation that the camera is mounted obliquely above the conveyor belt. In that situation, we have got two options. Either try to prepare algorithm for such deformated image, or we can remove this distortion using the calibration and then work on images like we have got a camera pointed or mounted parallel to the conveyor belt. Okay, so once we know when we should calibrate, then how to do that, how to perform that operation. For that case, we need a calibration grid. A calibration grid can be chessboard or can be a circle board. It's important to have a known pattern because the calibration itself is showing or is presenting a known pattern for the camera, and then inside the software tracking information about the deviations from this known pattern, and basing on that creating a camera calibration model. Okay, and the guidelines for such a calibration grid. First of all, it has to be accurate. When we are in case of very precise measurements, we also need a very precise and accurately produced calibration grid. For some applications, using a standard inkjet printer may be enough. However, we have to take into consideration that very often the scale along X and Y axis are not equal to each other. Another problem related to the just piece of paper is that it's not rigid. We may experience some, let's say, hills on this sheet of paper, and it will not represent accurately our working plane. Two more requirements. We definitely need a good contrast so that, for example, we have got a black dots on the white background or opposite direction. As a rule of thumb, we should have about 100 levels of brightness difference between the foreground and background. Also, the features on the image on the calibration board should not be too small. A good assumption is that the circle diameter should be not less than 20 pixels. And finally, the calibration should cover our entire working area. It don't have to be one calibration grid. We can combine a number of pictures. However, in order to achieve a good results across entire image, we should give the algorithm a calibration grid appearing on each position on this image. Okay, so now let's go to the practical example. As you can see, that's how my setup looks for now. And I will switch to Adaptive Vision Studio, and here we will be acquiring data and performing the calibration process. I have got a GigiVision camera, so I will add it to the program. I have to specify its address. It's the first one. And when I run the program, I can see that is my calibration plate. Yes, you can see I'm rotating it right now. So let's save the images. Give me a second. I have to find some good place to save that images. Okay. Image 1. As you can see, my calibration plate is covering almost entire area, so that it's enough to make 2 pictures. However, later we would like to also calculate the focal length of our camera, and for that case we need a calibration board presented at some angle to the camera. In this case, I will use some boxes and present the calibration grid at some angle. Okay, we have got one picture with that side. Let's make another picture. Fourth, and maybe I will take one more box so that it will be at much greater angle now. Yes, you can see how it looks on the image. Okay, I acquired 5 images. It should be enough to perform the calibration. So now let's add a filter, a tool for calibration in Adaptive Vision Studio. I will go to the Computer Vision 2D to remove distortion group. Here I have got a rectify image. Let's add it to the program editor, move it to the right section, and connect the out frame within image. Then we can see that there is still a question mark close to the in rectification map. So let's specify this map. When I open it now, I have got a GUI, the GUI for the user, so that here we have got 3 steps for creating the rectification map. First, we are on the camera calibration step. So we have to load the images here. I will select the images acquired a minute ago. Okay. And first I have to detect this grid. I will use a ruler to measure the diameter. Yes, it's about, let's scroll a little bit, for example here. It's almost 20 pixels. So let's set that the circle radius 10 is fine for us. And as you can see, I got detection, correctly detected calibration. You can see that these few dots were not detected. However, it's not a problem because on some other pictures, this area has been covered. You can see also how it looks for the distorted images. We see that here some kind of dirt has been also detected. Maybe we'll try to increase the threshold. Okay, now the dirt is removed. Okay, once we have got the image, once we have got the holes or the circles detected correctly, we can specify the camera parameters. In this case, I have got a pinhole lens, so that we'll use a projective model. For the telecentric lenses, we would use a orthogonal projection. Oh, I changed the parameter, so I have to localize the grids once again. Then I can specify the focal length. However, once I use a calibration grid mounted at some angle, then I don't have to do it. The algorithm will calculate it by themselves. And finally, I have got three distortion type available. The first one, the divisional, is the simplest one, and it works good even if the calibration grid is not covering the entire image. However, it's good rather only for a robot guidance application, especially for that don't require the extreme precision. For most of the cases, a polynomial model or polynomial distortion type is fine, and for the telecentric lenses, a polynomial with thin prism is perfect. Okay, we can compute the camera calibration model. And as you can see, we are getting information about the RMS of our calibration. The average RMS is below 0.1, which is very nice. The maximal is 0.8. Probably we got also some dirt somewhere, and it a little bit influenced the calibration. Or, however, it's not a problem for us. You can see also that these red arrows show where is the center or where should be the center of each dot. Okay, let's jump to the presentation for a second. So here we are talking about the camera calibration, the first step of creating rectification map. And here we were evaluating the intrinsic camera and lens parameters. What are these intrinsic parameters? That's the focal length of our lens, that's the distortion coefficients, as well as the principal point location. This operation, in fact, is closely related to the lens and camera setup and can be prepared in advance before moving to the production facility. However, any changes in the camera setup will void the parameters. So it's important to make sure that the zoom, focus, or aperture has not been changed, because otherwise we'll have to perform this operation once again. Another example or another operation which will void the parameter is replacing the lens, replacing the camera, screwing and unscrewing the lens. It may influence a small differences to the real case. Of course, it always depends on what are your requirements. If you are not creating a very precise application, then you don't have to be such strict on that cases. Okay, on the second step, we will be computing the word to image transform. So here we are combining the camera coordinate system with the word coordinate system. In this situation, we have to specify either the distance between our points on our calibration plate, or, for example, for the robot guidance applications, we have to specify at least 3, but it's good to specify 4 points for defining our for combining the robot coordinate system with image coordinate system. And once again, when should we repeat this operation? We should repeat it every time we change the camera position, every time the camera will be bumped or some other problems with the mounting element appears. Also, when the distance to the working plane changes, in that case as well a word to image transformation should be computed. And for the robot guide application, I suggest you using a circle board with some characteristic points, and inside these points also a small hole, because to this small hole we can use a calibration pin and precisely navigate the robot there. Okay, let's go to the adaptive vision and compute this step as well. Here I have to specify only the calibration grid which is presented flat of our inspection plane. So I will use a labeled grid so that we'll localize our grid correctly. And in this situation, I would like to use I would like to specify the circle spacing, which in my case is 2.5 millimeters, because I'm creating the gauging application, not the robot guidance. Okay, once we specify the values, we'll turn off the invert word y-axis because it's sometimes necessary for robot guidance, and I can compute the transformation. Okay, here we also got information about the reprojection error. In this case, it's even lower. Finally, on the third step, we are generating the rectification map. So here I will select once again our input image. You can see that these green borders specify or show how our image looks. That you can see that the edge of this frame is not parallel to the image frame. So we can clearly see that this lens also have some kind of distortion. However, it's 45 millimeters lens. Here we can specify the different options for our image. However, I will select the default one and I will generate the rectification map. Okay, so I have got my image after the rectification, so that now I can create a application and measure the diameter of my washers. Right, you can see how it looks. So I will add a tool for the okay, let's put it somewhere in the center. I will add a tool for circle for edge detection. I will connect the out image with in image, and I will also take the word scale inverse. Then I have to add a formula. So I will connect the out circle, and I will take the out word scale inverse. Okay, and here my out diameter equals in circle dot radius times 2, times in word scale. Okay, but you can see that we have got still some question mark here. So, oh, I don't have the image. So I run the program. I got information that something is missing, but I don't care at that point of it. And I will specify the fitting field. So I will be looking for my circle in very broad range. Okay. And now when I run the program, I'll take out circle to the preview. Oh, I see that it is not working correctly, probably because I have to change the edge transition. So I will change the dark to bright. And now we can see that it is presenting the data. I will split the preview and I will take the diameter to the bottom preview. Okay, so here we have got about 24, and that's information in millimeters. So let's compare it with the information which I have got on my slides. Okay, that was step 2. We skipped also the step 3. And I have got images of my caliper, and let's compare it with the achieved results. So for the bigger washer, it was 24.76. And on the adaptive vision side is 24.77. Okay, we have got some, it's a little bit higher. However, it's probably because of that the washer is has its height, and I don't take it into consideration. However, I would say that the result is pretty good. And let's change for the small washer. For the small washer, we have got the 19.622. And what we have got on the PowerPoint? 1971. Okay, we can see that here the difference is a little bit bigger. Let's change on the, let's check where we have got to position it. Okay, so you can see that here the difference is a little bit bigger, but it's probably because of some lower precision during this presentation. So definitely we are able to achieve a very good result using this calibration, and it only depends on your requirements and on what is your application. Oh, interesting. Okay, for the big one, I have got a good results, and for the smaller one, I have got a worse results. Let's take a look at that once again. (19.64), and when I take a caliper and measure that object, okay, I will present you the caliper under the camera. However, I have to increase the exposure time because it's not well visible here. So give me a second. Acquisition control, exposure time, and let's add one more 0 here. Okay, I have got my washer, and you can see that the result is about 1966. So probably I measured the different washer at creating that image. Okay, I will put it back here. As you can see, now we have got overexposure image, so let's change it. Okay, and over we are detecting our circle. Here we are detecting our circle. Is it fit correctly? Yes, it is fit correctly. Okay, I think you got a basic understanding of what is camera calibration, and now you will be able to utilize it on your applications as well. If you have any questions, feel free to ask me. Thank you very much for your attendance.